So for our next presenter, we'll have Michael Panis here for us. So Michael's a senior systems engineer at Teradyne, where he's been developing semiconductor test instruments for over 30 years. He specifies and architects high-density precision instruments that cover a wide spectrum of semiconductor devices requirements and enables faster time to market. So today, Michael is going to be discussing AT testing of the Tessent Streaming Scan Network on Teradyne's UltraFLEX platform. So please welcome Michael.
Once again, my name's Michael Panis. I'm from Teradyne. I'm a test guy. And so that's what I'm going to be talking about today. Anyone go to Paul Swanson's training yesterday on SSN? Raise hands. Okay, good group. Actually, so I know who I'm talking to. How many of you know enough about SSN that if I mention throttling, you'll know what I'm talking about? Cool. Okay, so I can breeze through some of these slides. Like I said, I'm a test guy. I'm going to be handling this from a slightly different angle than Paul was talking about. I'm going to talk about what are some of the considerations of taking a chip with SSN and actually trying to test it on a tester, AT tester. So as a test guy, there are kind of three things when it comes to scan that I really care about. And the first has to do with how fast I can get data into and out of the part. How much data in a given unit of time can I get that data in and out? And in the past, we've always been limited by how fast we can shift things through the clock, shift things through the device, as well as how many pins. The second thing that I care about is how much data is there, because all this data that we're using for all our patterns consumes memory. And people get really unhappy when the tester runs out of memory. So the less memory you can use, the more patterns you can throw at it, and the better quality you can achieve. Then the third thing I really care about is that any new technique, whether it's SSN or something else, is not so complex that you can't use it. Because we really want people to use our testers to get their products tested, find the working ones, and get them out to market. We don't want test engineers getting frustrated, pulling DFT engineers in the middle of the night to come onto a tester and look what's going on. We want it to be easy to use. And all these things are reasons why SSN is kind of cool to me as a test guy. So I'm just going to hit on some of the qualities of SSN that I think are pretty cool, but also they affect test. I'm going to go quickly because it looks like a decent number of people here know what SSN is. Getting data through the part, it's always been our limitation. You can only get that data clocked through the test structures at something like 100 megabits, I think is sort of a good rule of thumb. And SSN lets you get data in, same amount of data in on fewer pins, much faster rate. So you can get the data in much less time. It distributes it throughout the chip. And so you're still testing the chip at whatever its fundamental rate it could be tested at. But you can get the data in. You can test much more in parallel in the same amount of time and really increase the coverage you're able to get in that same amount of time. Hear a lot about SSN. It delivers pure payload. And so this shrinks down, I mentioned memory size, this shrinks down how much memory you really have to throw at the device. We get rid of a lot of the extra cycles that would happen between payload. Sort of stolen from one of Paul's slides, but one of the historical problems is you're testing, if you want to test a bunch of cores in parallel, they have to kind of run synchronously, which means you're always waiting for the slowest one. And one of the neat things about SSN is it says, I'm gonna do throttling. Remember I mentioned throttling before. I'm gonna do throttling, which allows me to essentially shrink down the overall time. In terms of sort of complexity you're no longer thinking so much about how many channels have to be used for each core. Fundamentally, you're going to set up your SSN bus with however many channels you need, and then it kind of takes care of everything else. And if, for example, you had, I don't know, I'll make up a number, 17 channels that you needed to get in, and you've got 8 bus pins, those numbers don't quite, divide into each other. And the easy way would be to say, okay, I'm going to find a common denominator. I'm going to throw just some extra cycles at it. So instead of 17, I'm going to add some extra cycles and get 24. 8 divides into 24 nicely. You don't have to do that. SSN just takes care of it. But one of the ramifications of all this is that data for a particular virtual channel, for a particular core, can show up on any pin. And that makes tests a little harder because we always used to be able to say, okay, this pin failed, this cycle failed, I know what's going on. Now this pin failed, and this cycle failed, and it could be any of the cores I'm testing, and I don't know what to do. So we had to get through that. And then finally, we've got this on-chip compare functionality. More and more devices have many instances of the same IP. And Paul mentioned yesterday, went through in detail some of the challenges of using traditional scan and trying to get IP, like multiple cores, to share the same data. It just doesn't work. SSN has a built-in mechanism that lets all the cores share the same data, radically decreases the amount of data that's required, increases the amount of memory that you have available for gaining coverage. And my final reason why I think SSN is so cool has to do with the complexity. Trying to get a chip tested is a long process. Not the actual test time. The test time's short, but it involves a lot of different people. You're designing a chip, putting in the DFT, then we're going to Siemens tools to try to figure out what patterns we have to throw at it. Then if you're using, for example, an UltraFLEX, a Teradyne UltraFLEX tester, there are other companies who translate all this stuff into something our tester can understand. Then we've got Teradyne, who's got to actually throw this data at the chip and read what's coming out, figure out pass, fail, and store it in some way that it can be understood. And then we go back to Siemens, and Siemens says, aha, this is what I see. Let me tell you which flip-flops were bad, or whatever. Okay, so what I'm presenting right here is the standard workflow. Pay attention, because I'm going to flip to the SSN workflow. It's subtle. That's it. Okay. Remember I mentioned complexity. Again, I don't like complexity. It's the same workflow. You're still using the same types of patterns. Yeah, they're going to look a little different. The data is going to be in different places. And in some cases, the diagnosis software, we're still putting data into a chip. We're figuring out what pins and cycles fail. We're providing that back to the diagnosis software. It can still figure out what went wrong. So that's pretty cool. You could do all that and not have to make any changes. Okay, if you're going to use on-chip compare, there's some changes, but pretty much that's all you need to do. And so thank you very much. I'm not done. I wish it were that easy, but there are really some challenges with SSN. They fall into a few categories. One is you may actually want to know which cores failed, and your test program may have to bin those cores differently based on bin the device differently based on which cores failed. You may actually even want to change the flow of your test program based on which cores failed. You may be doing some characterization, and you really only want to look at one core. Maybe you're changing the power supply level. You don't want to see that all the other cores are failing. You're focused on something. So you need a way to kind of mask all that other stuff out. There may be reasons you have, for example, redundant cores, and you know the core's failing, so you want to turn it off. And then there's this on-chip compare function. So I'm not done yet. So we've been working with Siemens for, I think, 1.5 years, 2 years to try to make sure that this all goes smoothly for everyone who's trying to use that ecosystem. We heard that a little while ago, that ecosystem of Siemens and Teradyne's products. And so what we've come up with is that in the style and wiggle files that Siemens software creates, there are annotations, and the annotations provide enough information for the tester to be able to identify when something fails, what core was related to that. Then as we create the patterns in the usual process that we always use, we're going to extract those annotations, essentially create some other files that we can use so that when we are running, we can actually identify not just what pins are failing, what cycles are failing, but also what cores. And we build into our tester software APIs that understand SSN, that understand this mapping. And so with just an extra line in the code, you can read back what cores failed. And I don't think, whether you know our programming language or not, I'm taking a guess you can figure out what's going on there. Just say failing cores equal, hey, tell me what failed. And then you can, whether you're doing further code, you're doing binning, or you just want to see what happened, you can just look at these variables, and it'll tell you for each site, these are the cores that failed. Pretty nifty. Okay, what about this masking problem? I want to tell a core to shut up. What do I do? We've built into our system the ability to turn off individual cores, multiple cores, whatever you want, and pay attention to just what you want to pay attention to. Again, we've tried to make this as simple as possible. So we take that same statement, hey, what cores failed? We have this thing called a mask. Apply that list of failing cores to the mask, and now all the failing cores will no longer fail. And I can start, for example, lowering my supply level and see if the core that is not masked starts to fail. It's all handled, since you're doing parallel tests, you're testing many devices at once. Just like almost everything else on our platform, all the sites are handled in the background. You never even have to think about it. The one line takes care of all sites, recognizes that different cores will have failed on different sites. Let's talk about on-chip compare. One thing to realize about on-chip compare is that if you had 100 instances of a core, it's not like 100 instances are all going to share the same data. We're going to divide things down, or SSN is going to divide things down into groups. And each of those groups will end up sharing information. Now, the other thing that changes with on-chip compare is that usually you would put some data into the part, you get some data out, and you say, and then you know what to expect, and so you would figure out, oh, did I get the right thing? With on-chip compare, the chip does that for you. The SSN within the chip does that comparison. So instead of just putting data in, we also have to put in the data, put in, here's the data we expect, and a mask bit that says, do I care? And the chip determines which cores or which groups passed and failed. It's also continuing to put data out, which we can capture for data logging. But there's a little problem here. Since multiple cores are sharing the same data, if, for example, as I've shown here, core 2B fails one cycle and core 2C fails another cycle, I see two failures. I don't know which core failed which. That's not really very helpful for diagnosis software, so got to come up with something else. So SSN has built into it these two things. One's called sticky bits, which is basically an accumulated fail. for every core, not just a group, but for every core, did that core fail? And the other is called contribution. Contribution says, remember that output stream that we want to use for diagnosis, which cores are going to participate in that output stream? And you can turn off a core's participation. These sticky bits and contribution are like device registers. We can write to them, we can read to them, just like we set up IJ tag stuff for the rest of the device for the scan pattern. We can figure out what's going on with the sticky bits. We can set the contribution bits. Well, how do we figure out what to do? Again, Siemens annotates the style file. And again, we extract that information. So you never really have to look at it because we're going to do that. And so when you say, I want to enable a core, disable a core's contribution, or figure out which cores are passing or failing, we look at the data in those files and kind of take care of it. Now, because you've got multiple cores sharing one output bit, if you want to do diagnosis, you got to repeat things. The data that you got the first time, you can't use for diagnosis. So if I want to run diagnosis on these individual cores, I'm going to have to reburst the pattern. And that may seem like all the benefit of on-chip compare just got lost, but it's really not that bad. The way this works is you burst the pattern once. If it passed, you're done. It passed. That's great. I don't have to do anything else. It passed. If it failed, I go over to my red box, my horribly red box here. And by the way, this is only if you plan to run diagnosis. If you're not running diagnosis, if you're just doing go, no go, you don't have to worry about this. But if you're trying to do diagnosis, then you read back the sticky bits. You go through all the groups and you say, did any group have more than one core failing? As long as no group had more than one core failing, you're done. All those output streams are legitimate. They can be used for diagnosis. In the event that you've got more than one core failing in a group, then you end up writing to the contribution. You kind of loop through your groups, write to the contribution register, burst again, get the data you need for your diagnosis, then go to the next core and run that one. So it's kind of, as long as most of your chips are working, no time added. In order to get this to work, in addition to the mapping, in addition to reading in those mapping files and to figuring out what to do, we had to figure out how do we get this information back to Siemens in a way that they can actually diagnose it? Because now we're going to go from one burst to possibly multiple bursts. And so what we've done is we've come up with a agreed upon methodology to put certain information into the data log file, both in the scan test records and in the data log test records. And we can indicate, was this first burst? Was this one of the rebursts? Which cores failed? All the information that Siemens needs to figure out, to diagnose the part. Conclusions, I'll go quickly to leave some time for questions. SSN's really cool. That's my basic summary on that. If you're going to do things like bin by core, characterization, stuff like that, we've gone through this, we've figured out what needs to be done, we've built things into our tester for that, we've worked with Siemens so the whole methodology flows. On-chip compare, really cool part of SSN. Can super decrease in the amount of data needed, amount of time needed. Again, if you want to do diagnostics though on it, you got to do some extra things in the program. And again, we've worked with Siemens closely to make sure that we have the necessary things built into the tester to allow you to do that and to do it in a non-complex way so that you're not spending a lot of time trying to figure out what SSN is You're just dealing with things like which core failed, or which core do you want to turn off. And then we've agreed on how we're going to report that information back for data logging.